Hi, this is Flavio Corpa from 47 Degrees, and along with my colleague Alejandro Serrano, we'll be presenting this experience report together about describing microservices using modern Haskell. We're going to introduce our library, Haskell, sponsored by 47 Degrees, and basically it's just a library to develop microservices. We had two goals while developing this library. We wanted to support a wide range of formats, and right now, for example, we support protocol buffers and Avro for serialization, and as transport layers, we use gRPC and GraphQL. And we're working right now also on JSON serialization to support OpenAPI, which is going to be an interesting challenge. Also, our second goal was to use type level to encode our schemas and services. So we wanted to leverage the type superpowers of Haskell and try to encode on the type level as many things as possible. Also, we need a bit of context. So why the name? Muse is a family of libraries that originated at 47 Degrees. And the first Mu was in Scala. You might know of it. It's called Mu Scala. And Mu Haskell is like the second incarnation of this family of languages called Mu Haskell. But there are other Mus to come. Hopefully, for example, we'll see Mu Kotlin and maybe Mu Swift in the future. Who knows? And the approach we take on every implementation or on every incarnation of the library is to provide idiomatic solutions. Rather than being a port from the same library to different languages, we try to use idiomatic solutions to the same language. For example, the type level encoding stuff, it's only from the Haskell, the Mu Haskell version flavor, but Mu Scala uses a different approach. And the common point we have is that we treat our schemas as the source of truth, and then we generate the code either in Scala or in Haskell coming from those schemas. And of course, we are also aware that there are other things called Mu, like the Mu compiler for Haskell. Maybe the name is a bit unfortunate. We apologize for that. And also the Mu calculus. But well, we're not going to discuss that. So for example, let's have a service description file as in protocol buffers as an example. We have two messages, a person request, which contains an ID, and then a person with a name, a field name, and an age. And then we have the service declaration, the person service, which has two methods, the getPerson and a new person. GetPerson receives a person request and returns a person, and new person receives a person and returns the person request. And this is key to interoperability with other systems that use gRPC. So to achieve this in Mu Haskell, obviously you need to enable 1,000 of language extensions. We're sorry for that as well, but we're all used to that right now. And the only thing that you need to do is to provide that line in, say, gRPC, the name of your schema that you want, the ID function that you will see later, why it's needed, and also the name of your protocol declarations file. And this will basically generate two things. All the messages will be separated in, all the messages will become types, and the service declaration will become its own type. So for example, the messages, person request and person that we saw in the beginning are going to be part of the type person schema. And this is the type level encoding. It will be represented in, and the methods will belong to the person service. And we'll see that they have a name method, getPerson, and also the type of arguments that it receives and the type of return that it has. And also the method new person acts the same way. So person schema describes the shape of the data. And the terms that we use internally in Mu Haskell are the interpretation for those schemas. So for example, here's an example of a person encoded in the type level, in this case, Alejandro and myself. And term, the interpretation, we use underneath GADTs to form the terms. So as you see, maybe this encoding is not so nice and it would be very hard to type. But what we did with this line of gRPC is basically we leverage the use of template Haskell to, coming from the service declaration files, generate all this type level encoding so that you don't have to do it. So that's a plus. And this way we managed to bring generic programming into the industry, which we're very happy for. So what else? Well, our encodings are related to a sum of products. We basically encode fields as type level lists, and we also use mutual recursion by making each schema its own enclosed universe. So that way we achieve deep embedding in the terms, which is something that was hard to manage otherwise. But obviously, there is no joy without pain. So we managed to bring some ideas from academia into industry. We leverage the use of type level programming. We also use data type generic programming all through the code base. And we had an interesting challenge with GraphQL while we were implementing the server for GraphQL, because GraphQL doesn't have this separation of concerns between the services and the messages. So while developing, we could introduce another academic research called attribute grammars. And hopefully, maybe we will borrow some other ideas from academia in the future. And of course, we found some weaknesses in Haskell itself and on the approach. And this is basically the experience report in which we tell what are the lessons learned from this project. And for that, let's talk about these trade-offs. And I'll leave you with my colleague, Alejandro.
Thanks, Flavio. Indeed, we found several weaknesses while developing Mu Haskell. The first one is related to type application and proxies. Let me show an example from the library. From a service definition, one of these big type-level encodings of what methods, arguments, and result types are coming from an RPC service, we can derive a client. We have two different mechanisms to do so. First of all, we can use type applications, and from those we give the reference to the service and the name of the method. You can see that we use the @ symbol in both cases. That's how we say to the compiler, well, this is the type for which we want you to instantiate the method grpc call. Another possibility, if you don't want to go into type applications, is to use the well-known friend of Haskellers, proxy values, which allow you to have information about a type encoded as a term. However, we found that this is quite hard for beginners. They always wonder what this weird @ symbol, why do you have strings there? And why do you need to have proxy ... proxy person service? Also, type application is not completely first class. For example, we could not use flip to say that we first want the name of the method and then the service where this comes from. So this is something which, is different from what you are used when using Haskell. Fortunately, for this case, we found a solution using optics and a feature in GHC called overloaded labels. A call to a client can be written like this in Mu Haskell. The caret dot is the get operation of optics, and what we do is we create a new optic called hash get person using what it's called an overloaded label. An overloaded label is nothing else than a nice way to deal with type level strings, and in fact, when you write hash get person, the compiler translated to from label add string get person, but it looks a bit nicer. Actually, it looks close to what an object-oriented programmer would write, something like client.getPerson. And the fact that there are no strings looks like this thing is actually checked by the compiler what it is, even when it was a string, but this gives, the feeling that there is some checks being done, not just passing a random string. So what we have here is kind of extensibility with a nicer syntax than the type applications. In fact, we hope in the future to rework this once the record.syntax extension comes into GHC, and then we can actually write client.getPerson, because things after the dot are going to be extensible in a very similar way to what overloaded labels is. So our takeaway here is that for a language to be nice for this kind of frameworks, what you need to provide is extensible syntax which integrates well with the rest of the language so it doesn't look weird, and also resolves guided by some kind of type level mechanism. So here the fact that getPerson works is mediated by the fact that getPerson is one of the methods in that service. So everything is still compile time check. The second pain point is related to GEDTs. GEDTs are very used nowadays, and for example, we use them in Haskell to define a server by composing several handlers. So for example, where you define the server for this person service we've been talking about the whole time, you say, well, you have a handler for the get person, a handler for the new person, and then you have to end with 80. This is actually it's essentially building an heterogeneous list, and we've got the inspiration for this from Servant, which is a very nice library for building REST services in Haskell. So we are porting this to the arena of microservices. But it turns out that providing such a strong API can also be a curse. For example, if you forget to add the final const 80 or swap or forget the handler, what you get is a very scary error message. So problem is not that this API is not nice. If you make a mistake, it's very hard to point out where the mistake is. And remember, we want this to be useful for beginner, intermediate Haskell users. We don't want you to have to be a type wizard in order to use Mu Haskell. So this uses of JDT has actually beaten us several times because of, as I said, the weird syntax and the fact that if you make some mistake, the error messages are quite hard. So what we do is we added some additional functions called server and method, which essentially match at compile time by checking the service definition. So here you have the server definition that I was showing before, but where you can actually swap the order of the method new person or the method get person. So what we did is we encode the search of each handler. So we make sure that each handler is present by doing a search at compile time. And the nice thing is if one is missing, we can fail with this customized type error. So we can show the error message we want. So essentially, we are sort of overriding the default working of the compiler. And this is something that we've seen could lead to better error messages. By the way, at this point, if the compiler had also support for sets, that wouldn't hurt either, because many of our problems are actually related to the fact that these handlers are more a set than a list, but we have to encode the fact that they are sets by using a list and then searching every type. The third problem is related to how we use type classes and how we define new type classes. There are actually two problems into one. So let me start with the first one. So inspecting the service definition, the fact that we have to match all of this is done with type classes. Why type classes? Well, because that's the only way that Haskell allows us to do some compile time check, some compile time computation, which actually reflects into the term level. So we have some runtime behavior by using the elaboration. So think, for example, finding the handler for a request, where you actually want to do the search also at runtime to find which is the right handler. However, if you look at the code we wrote, you will see that actually we have a lot of sort of pass-through parameters. So I have here an example called run method, and this run method, it's only actually checking the name, so this S name, but because it uses other type classes inside of it that need whole or chain or something like this, they need to pass through the things. So you might be wondering, why do we need so many here? Why are we passing all of this? And our conclusion is that there is a big difference between term level and type level in globality and locality. In term level programming, you have local binding, so you can have this function fxy, which calls g, and g somehow uses the x, which is provided there. So it allows you to access some information which is made available in a scope, but actually you don't have to pass the x to g again. However, if you use type level programming in Haskell, there is no such facility. So for example, if we have fxy, and then we sort of pattern match by having several instances, and one we are using g, which needs x, then we need to pass x again. And this builds, it builds bigger, it grows bigger and bigger as you have more parameters, and that's why we need to have all these parameters. What we would really like is to have some kind of local scope for this type classes in which you can share some information, and then, maybe like the whole service you're inspecting or things like that. The second problem with type classes is that they lack abstraction mechanism. In fact, type level programming in Haskell is essentially first order. You don't have maps, you cannot have folds over type structures. It's hard to get something like closures because, as discussed above, you have to pass all the information. So that means that in our code base, we end up duplicating code which traverse services definition over and over. We have things which are essentially a map or a search, and it could be written with lem if we were using term level programming, but we have to write it over and over because we are using type level programming. The other thing is that once you do type level programming, matchability and the order is extremely important. And with matchability, I mean that type families in principle are saturated, where type classes may not appear saturated, which is a big difference. There's work on matchable families, but as far as I know, it's still work in progress. But even with type classes which may appear unsaturated, the order is extremely important, because once you fix this order, it's very hard to reorder this. There is no such a thing as a flip. So if you try to have a map, and then your map has to work with something like a type function, but where the second argument stays the same, but the first one changes, it's going to be extremely hard. So this lack of abstraction mechanism is actually hurting us when writing sort of more maintainable and not so duplicated code. So we have some ideas of how to move forward here. So we consider dependent types. This might be a good solution. The problem is, of course, that Haskell has a rich ecosystem of libraries which already provide gRPC and we have ASON to trace into JSON. So we can build on top of those when building our own library. Whereas in most dependently typed languages don't have yet this rich ecosystem. The second question is how to ensure that type inference does not suffer. Even if we go to dependent types, well, dependent types that have less type inference, and we want some amount of type inference because, well, that's what Haskell expects. Actually, talking about type inference, let me show you one of the scariest error messages we found. So imagine we have something like I shown before, a server with two methods, and we say, well, I have the handler for the first one, but I will leave the second one unimplemented for now. So we do as any Haskeller would do, we write undefined there, and boom, we have this big message which says something like ambiguous type variable prevents some constraint. It's a big error message which shows a big type. I'm not printing here, and it's actually very scary. It doesn't point out what's the problem, what it's missing, why the compiler cannot solve that constraint. Actually, what happens is that by not writing the code for the handler, by having undefined, some types are left underspecified, which means that the compiler is not able to resolve the correct realization instance, and boom, the compiler doesn't know which instance to choose, so it shows an error message. It's even worse that in this case, the choice actually doesn't matter because we have just undefined. So if you ever call this, everything you will get is an exception. So actually the choice does not matter, which of course does not hold in general. In general, this choice might matter, but it points out how by doing something which is common in Haskell and nobody expects to break, you actually have problems because of, well, the type inference. So what we see here is that GHC is sort of working towards having better error messages for wrong programs using type errors, but there is a lot to be explored yet for underspecified programs. So things when some types are ambiguous, or maybe some counts are ambiguous, don't have the same level of support. And actually, I think that's kind of an interesting research question, how you should do this, or how programmer of a library can steer the compiler into maybe fixing some of these ambiguous type variables in the same way that sometimes when we are dealing with the GHC interpreter, we fix some of the type variables to int or to unit, because otherwise it will be very cumbersome for the user to type the whole to fix the whole types. Well, so that's all. In summary, Flavio and I have presented Mu, which is a library to develop microservices. So you are more than welcome to go to our webpage, try it, look at the code, raise some issues. Something what we found it's very interesting is actually a lot of information can be represented at the type level. That's a well-known thing in the Haskell community. But I think we move a step forward by actually importing this information from other sources. So we take that sort of typing information in form of service definition or schema definition, which already circulate in projects, and we read this and turn this into something which Haskell can reason about. The main part of our paper, of course, is how to improve type-level Haskell. What are the stumbling blocks we found when dealing with modern type-level Haskell. And the main points we raise are that GDTs and type applications are actually hard for beginners, so we might look at other possibilities, like, as I mentioned, extensible syntax, which integrates nice with the language. Also, type classes, and this also holds for type families, are too global and lack ways to abstract. So you end up repeating and duplicating a lot of code, which essentially traverses type level lists or matches or looks for elements. And the last point has been about ambiguous type variables. And what we find is they actually destroy good error reporting. So there is a lot of work to be done from moving from type error into something like, well, defaulting types or ambiguous type variable. Well, it's been a pleasure to talk to you. Thanks for listening, and we'll be happy to hear your questions in the corresponding Q&A session. See you there.